Welcome to the deep dive. Today, we're exploring something pretty amazing, really, this unexpected link between a huge volcanic eruption in 2022, the Tonga one.
Right, Hunga Tonga, Hunga Hapai.
Exactly. And how that single event actually tells us about, well, billions of years of Earth's history, why our continents are stable, and maybe raises some flags about where we are now.
Yeah, it's fascinating. We tend to think of Earth as, this solid, unchanging backdrop. But the sources we're looking at today really show it's this dynamic, sometimes turbulent, interconnected system. So our mission for you listening is to kind of cut through all the data from this eruption.
There's a lot of it.
Oh, tons. And get to the core idea.
Yeah.
The planet is constantly in motion in powerful ways we don't always see.
Definitely. That 2022 Tonga eruption wasn't just some big explosion. I mean, it was possibly the most powerful one we've ever measured properly with modern instruments.
Yeah, in the instrument age, absolutely.
And it sent these shock waves, actual physical waves, that went around the whole planet, everywhere from the ocean surface right up to the very edge of space.
Incredible reach.
So today, we'll focus on two, maybe surprising, ways this one event gave scientists almost like an X-ray view, deep inside the Earth and high up into the atmosphere. And so let's dig into that shock wave first. A volcano in Tonga. That's what, 6,000 miles from Alaska?
Roughly, yeah. South Pacific to Alaska.
How on earth does an explosion there literally make the ground shake thousands of miles away in Alaska? It sounds almost impossible.
The scale was just immense. The atmospheric pressure waves from Hunga Tonga were the biggest we know of from a volcano since Krakatoa back in 1883.
Wow, okay.
But the key thing here wasn't just the size, it was the type of wave. They were mostly long period waves.
Long period, meaning
They oscillate really slowly. So think less like sharp, quick ripples on a pond and more like huge, slow ocean swells.
Oh, okay.
And that slow, massive movement allows them to travel incredible distances across the atmosphere without losing much energy.
Right, they don't just fizzle out quickly, but how does that energy traveling in the air actually move the solid ground?
It's this process called air-to-ground coupling. Basically, as these really powerful low-frequency pressure waves move through the atmosphere, they cause these intense, rapid changes in air pressure right at the surface. And that wave of pressure literally pushes down and then pulls up on the ground.
Huh. Like the air itself is physically moving the land.
Exactly. It's transferring energy. Think Newton's laws. That push and pull creates new seismic waves within the Earth's crust.
Geez, it's like the atmosphere is ringing the Earth like a bell, almost.
In a way, yeah. And it was a really unique opportunity for seismologists. A massive global pressure source that just appeared.
A natural experiment.
Precisely. Researchers at the University of Alaska Fairbanks Geophysical Institute, they saw this immediately. They used that coupling effect to measure seismic wave speeds, specifically shear wave velocities, V's down into Alaska's crust.
Okay, hold on. For those of us not doing geophysics daily, what does measuring shear wave velocity tell you?
Basically, it tells you how stiff or soft the rock is underground. Faster shear waves mean harder, more rigid rock.
Got it.
And by using the Tonga wave, which was so powerful and widespread, they could measure these velocities down to at least 5 kilometers. That's over 3 miles deep.
3 miles down just from an atmospheric wave.
Yeah. And here's the key thing.
Yeah.
Older methods, using things like strong local wind, could only really probe maybe tens of meters deep. This Tonga event let them see, like 2 orders of magnitude deeper, a much clearer picture of the upper crust.
So it really was like a natural X-ray, as you said, unprecedented detail.
Totally unprecedented from this kind of source. But the energy didn't only go down, it went up too.
Ah, right. Connecting the deep Earth to the upper atmosphere.
Exactly. The same eruption generated this enormous wave that travels along the surface, an acoustic gravity wave called the Lamb wave.
Lamb wave, okay.
And this thing, it circled the entire Earth 4 times over 6 days. Again, the only comparison we really have is Krakatoa.
4 times around the globe. Just staggering. And you mentioned it reached the edge of space, the ionosphere.
It did. That huge pulse of energy moving through the atmosphere created ripples in the ionosphere. That's the charged layer way up high. They're called traveling ionospheric disturbances, or TIDs.
TIDs.
And scientists track these TIDs globally. They use data from over 5,000 GNSS receivers worldwide.
GNSS, that's like our GPS systems.
Yeah, global navigation satellite systems.
Yeah.
Your phone's GPS is part of that network. It showed just how sensitive that upper layer of the atmosphere is. It acted like this huge detector, showing the impact rippling across the globe.
So one eruption, thousands of miles away, connected the rock deep under Alaska to the plasma at the edge of space. That's quite a connection.
It really underscores the interconnectedness.
Okay, this is where, for me, the story takes a really interesting turn. If the atmosphere can shake the ground like that, what makes the ground stable enough to begin with? So we shift from this very recent event to the really deep history. Billions of years.
Wow.
How did our continents even form? How did they become stable enough to, support life?
Yeah, we pivot to the deep past now. We look at what are called continental cratons.
Cratons.
These are the ancient, super stable cores of today's continents. Think of the Canadian Shield, parts of Siberia, Western Australia. They've been solid and stable for literally billions of years.
Okay.
But how they got that way? Well, new research has flipped the script a bit.
Yeah.
It turns out the secret ingredient wasn't just gradual cooling, as maybe you'd assume. It was actually extreme intense heat.
Wait, heat? To make something stable and solid? That sounds backwards. Wouldn't you want it to cool down?
It seems counterintuitive, right?
Yeah.
But yeah, researchers found that for these stable continental foundations to form, the lower crust, the deep part, had to get incredibly hot. We're talking temperatures above 900 degrees Celsius.
900 C, and that's hotter than previously thought.
About 200 degrees Celsius hotter than the models used to suggest was needed for this process.
So why? Why did it need to get that hot first? What did the heat actually do?
It basically powered a massive sorting process deep within the early Earth's crust. Geologists call it differentiation. This extreme heat mobilized certain elements within the rock.
Which elements?
Specifically, the heat-producing radioactive elements: uranium, thorium, and potassium.
Ah, the ones that generate heat themselves.
Exactly. The intense heat made them mobile, allowing them to migrate upwards, moving from the lower crust towards the surface.
So the heat essentially forced the Earth to shuffle its internal heating system around.
That's a great way to put it. By driving those heat sources up, it allowed the deep lower crust, the part that needed to become the stable foundation, to finally start cooling down effectively. It could shed its heat, harden, and solidify over vast timescales.
Creating that stable base we rely on.
Creating the stable base. And you have to remember, back in the Archean eon, billions of years ago, the Earth had roughly double the amount of these radioactive elements compared to today. So there was a lot more internal heat to drive this whole process.
Okay, this sounds like fascinating deep Earth history, but you hinted it actually matters for us now. How so?
It has a couple of really significant modern implications. First, resources. That same heat-driven sorting process didn't just move uranium and thorium.
Right.
It also concentrated other valuable elements, things critical for our technology today, like lithium, tin, tungsten, rare earth elements.
So understanding how continents formed helps us find minerals today.
It provides vital clues. Knowing the conditions under which these elements mobilized helps exploration geologists target where they might be concentrated now.
Okay, that makes sense. And the second implication, you said it goes beyond Earth.
Yeah, this is really exciting. It helps in the search for habitable exoplanets, planets outside our solar system.
How?
Well, this research suggests that this specific mechanism, getting hot enough internally to reorganize your heat sources, allowing the deep parts to solidify into stable platforms, this might actually be a kind of universal requirement for long-term planetary habitability.
So finding planets that might have gone through this hot sorting phase could be key to finding life elsewhere.
It could be a crucial filter, yeah. A planet needs that long-term stability. And that brings us almost full circle, connecting the deep past to the precarious present. We've talked about billions of years of stabilization. Now let's jump forward to the last, say, 12,000 years, the Holocene epoch.
Right, the geological period we've been living in. The stable one.
Exactly. Geologically speaking, it's been remarkably stable. Predictable climate, sea levels. It's been called the Garden of Eden for human civilization to flourish.
We know that stability is changing rapidly.
That's the crux of it. Human activities pushing the entire Earth system out of that stable Holocene state. That's the essence of the Anthropocene concept, the age of humans fundamentally altering the planet.
And scientists have ways to measure this shift, right? These planetary boundaries.
Yes, the planetary boundaries framework.
Yep.
It identifies 9 critical Earth system processes, things like climate change, biosphere integrity, biodiversity loss, freshwater use, land system change, and so on.
And how are we doing? What's the latest checkup say?
It's pretty sobering. The latest assessments show we've already crossed the safe operating space for 6 out of the 9 boundaries.
6 out of 9, that includes climate change, obviously.
Climate change, biosphere integrity, land system change, freshwater change, both green and blue water, nutrient cycles, nitrogen and phosphorus, and novel entities like plastics and chemical pollution.
So we've basically used up our safety margin in most key areas. What does that actually mean for the planet's function?
It means we're reducing the planet's resilience, its ability to self-regulate and absorb shocks. Crossing these boundaries increases the risk of triggering abrupt, irreversible changes, tipping points.
Like the Greenland ice sheet melting or the Amazon rainforest potentially collapsing?
Exactly. Those kinds of large-scale shifts. And the 2024 Planetary Health Check report indicated that for the boundaries already crossed, we're generally moving further into the danger zone, not pulling back.
It feels like a double hit. We're adding stress, like greenhouse gases, while weakening the systems that could handle that stress.
That's a perfect summary. We're pushing the accelerator while damaging the brakes.
It's interesting, too, thinking back to the deep Earth connection. Plate tectonics, the movement of continents, is often called the ultimate climate stabilizer over millions of years, right? Linking the surface and the deep interior.
It absolutely is. It regulates the carbon cycle, builds mountains, creates oceans. It's fundamental to Earth's long-term habitability. Even in the very early Earth, before modern plate tectonics fully kicked in, models suggest a different style. Maybe something called a sluggish lid regime.
Sluggish lid. That's slow.
Yeah, maybe less efficient, perhaps more like localized dripping or foundering of crust rather than large moving plates. But even that allowed the planet to lose internal heat and start forming that stable crust we talked about earlier. It was a necessary step.
So the planet's history is all about dynamic movement and change, which eventually, luckily for us, created this relatively brief window of stability. The Holocene.
A window that we are now actively closing through our own actions.
Yeah.
And that realization that we're leaving the stability of the Holocene and re-entering a period of, well, turbulence and rapid change has led some to propose a new term alongside Anthropocene.
Oh, what's that?
The Kinocene. From the Greek word kainon, meaning to move or to set in motion.
Kinocene.
So if Anthropocene highlights the human cause, Kinocene emphasizes the state. We're entering a return to planetary-scale movement, dynamism, maybe even chaos. A restless Earth.
Wow. Kinocene. That really frames it differently. So let's try and tie this all together quickly. An incredible deep dive today.
Yeah, it covered a lot of ground, from the deep Earth to deep time.
It did. So for everyone listening, the key points. That massive Tonga eruption wasn't just local. Its atmospheric waves shook the ground in Alaska, giving us this unique X-ray view miles deep.
Right, through air-to-ground coupling.
Then we jumped back billions of years to see how the very foundation of that ground, the stable continents, were actually forged in ultra-hot conditions. Heat that allowed radioactive elements to move up.
Letting the lower crust cool and harden over eons. A crucial step for habitability.
And that deep history has echoes today, helping find minerals and maybe even identify habitable exoplanets. But then the stark contrast, human activity now is creating a new kind of planetary imbalance, pushing us out of the stable Holocene.
Reaching critical planetary boundaries and entering this more turbulent state, perhaps the Kinocene.
Which leads us to a final, pretty profound thought for you to consider. We learned that billions of years ago, Earth's long-term stability, its habitability, was essentially bought by intense internal heat driving the movement and reorganization of materials, allowing the deep Earth to cool. That upward heat migration was key.
The prerequisite for long-term cooling success.
So what does it really mean that our civilization is now causing massive, rapid external heating and energy imbalance through greenhouse gases? Is this human-driven heat fundamentally challenging, maybe even starting to undo the planetary thermal stability that took billions of years to achieve?
Are we reversing the very process that made complex life possible?
A heavy question to ponder. Thanks for joining us on the Deep Dive.